Okay, we talked about the exponential distribution last time. So I want to very quickly review some of the things that we talked about. Um, I also want to go over some. Uh, yeah, let's talk about things that we discussed. Some of you have. Uh, okay. So the okay, let me get the display on first of all. We talked about the exponential distribution and we mentioned a few things. We've also proven some things and we've done some numerical examples. So we'll continue along those lines. Okay. So if you recall, the exponential distribution is a very famous continuous distribution. It's named. There are a few properties. We know it essentially looks like this. We did talk about this the last time, which is some people write this as 1 over lambda instead of lambda. If that's the case, then your expected value is lambda. I feel this is a little bit easier because it makes the integration less fussy, and the price you pay is that your expected value is 1 over lambda. That's all, right? But the rest is fine. We talked about something quite famous called a memoryless property, and basically it just says that for an exponential distribution, if I know that this has happened, if I know that it has survived, basically what is an exponential distribution model? It models time. And if I know that you have survived more than A hours, knowing that, what's the probability that I go on to survive more than B is actually interesting. The exponential has a memoryless property in that it means it's the same thing as if I just started existing and you just look at the time difference. If you think of it as drawing a timeline, zero is here, A is somewhere along the timeline, B is a bit ahead. Knowing that I've lived up to A, the probability that I continue to live after B is as if, in the mind of an exponential, it's as if I start fresh and just I'm born at time A and I live that small fraction of time like that. Now, that's not a very realistic model for many things in life, but it is a good model for some survival things like I think certain appliances behave like this. It doesn't matter how long it's been on. It's like every day is a new day kind of idea. I think I said that the last time, right? It doesn't remember the past. So the first thing I want us to do, this is a very simple problem. I want you to, it will only take you a couple of minutes. Can you prove this for an exponential? And to save us all time, don't need to keep deriving all the CDFs. You can please, I recommend, use this CDF. You know that for an exponential, the probability that you're less than something is given by this. So can you use this just to prove the memoryless property for an exponential distribution? Show this. In other words, show that this is true for an exponential lambda. All right. Again, you can get started. If you have this is an ICP, okay? Do it as an ICP. Show that this property is true for an exponential. And you can certainly use the CDF that we have here, this one. All right. This just tells you what? For an exponential, the probability that you're less than T, because that's what CDF means, less than a certain number is given by this expression. So that should save you time evaluating probability of being more than something. Okay, so give it a try. All right. Need help? Just let me know. All right. So to do this successfully, you need to know what this even means, right? You should by now know what's the definition of a conditional probability. Right? Just use it. This is honestly a 2 or 3 line proof. It's not something. You should not need to write any calculus. In other words, right? You should not need to integrate anything. Just go by the definition of conditional probability, and I'm confident you can do it. If you need any help, just raise your hand. I'll help you. Right? If you're confused about something or you don't know what to do. Are we doing okay? Because it's not a very, I'm very concerned because I'm not hearing much. It's not a very difficult problem. But are you all able to prove this? First, begin by breaking this down. What does this mean? Right? Remember, B is at least as big as A. So this expression can be simplified to something else. And then just derive what that is for an exponential distribution. Uh, yes. Yeah. So you have that views. Yeah. Yes. That is so again, I think what's holding up. What is this? Okay, what is it? If you say X is 1, and X is 1, and you simply compare this on one signal, it is which is a smaller event. I modify the score and I modify now. How do you use the CDF to really work with those two points? So because but not directly because this is what's the direction? So I think there's a bunch of things making you confused. First of all, the CDF always tells you the probability of being less than something. I know this whole thing is oriented in the opposite direction, but is that going to be a problem? Right? The CDF gives you less than, so you can change that to a more than statement by just modifying the equation. That should give you the right answer. Yeah, so oh, I know this is showing the wrong direction. Because the CDF tells you the other. Yeah. Not like that. So this is the definition of definition. So we already know that the.
Yeah, I know that.
So that
Why is that?
because this is top part. Because if we're saying X is greater than 5 and X is greater than 8, so that it just, we know that X is greater than 80. Because 8 is greater than 5. So then it just finish the proof. What is the probability that X is more than? So there's a bunch of things which I can see the class is not registering very well. So I'm a little bit, okay, so concerned because it shows that your understanding of a CDF is not that good. First things first, a CDF is always CDF is always defined as the probability of X being less than or equal to something. You need to know that. It so happens that for an exponential, this looks like this. First of all. Next. If I know this, can someone tell me what this is then? What is this? Can someone tell me? What is this? If this is this, what is it? That's right. This is not a CDF. CDF is not defined this way. But this is a very useful formula that you can use all day long to prove this thing. Because the whole point of the memoryless property is everything is orientated in this direction. So I don't know about you. If you want to write, if this formula is more useful to you, then learn this. But this is not the CDF. The CDF is this one. So this is an expression that you can use to actually show this property. And I think I will let you finish this on your own. Right? This is quite fundamental. If you really don't understand how to do this, you come see me and I'll help you. Right? All right. See, this is a specific CDF form only for the exponential. Not every random variable has this CDF. This is the CDF for an exponential. That is why the memoryless property is only true for an exponential. It's not true for every distribution. It needs to have this specific form before you can use it. So please make sure you finish this and understand where this comes from. Remember that sometimes when you prove something in math, even if you can't seem to go from A to B, you can work both sides until you get something common. That's a very big thing. I don't know whether you know this. Even if you can't go directly from A to B, sometimes you can work on A, one side, get something, work on B, the thing that you want to prove, and just meet in the middle. That's an acceptable way to prove this. All right. Okay, so let's go on. I think there's still an example which we did not finish the last time. This example was part of the ICP which I asked you to do. And let's get to that. And y'all did that well, okay? That was an exponential example as well. So let me call that out. This one. I asked you all to do part of the work and you all did it correctly. We checked the ICP that you submitted to me. The point is, first of all, tell me what the lambda parameter is. So let's solve the problem again. We know that 25% of the claims made to an insurance company is less than $1,000. What is this statement saying? This statement is saying the probability that the claim size is less than 1,000 is 1/4. This is a roundabout way in exponential problems where I don't tell you lambda, but you find it. So if you look at the ICP that I returned to you, you did it correctly. You wrote this statement. This statement says the probability that a claim is less than $1,000 is 35%. But for an exponential, this probability is this, again, with the CDF. Now the amount is 1,000. The parameter lambda is not known. And you can solve this to get lambda. And I think you got 0.0002 or something smaller, which is correct. Okay. Now, how do we answer this question? After we have established what lambda is today, the size of claims is still exponential, but owing to inflation, every claim made today is twice the size of a similar claim made 10 years ago. So look at how I define this. X was the claim size 10 years ago. This is the claim size today. What are we saying? Claim sizes today are twice what they were in the past. So I'm saying y is 2x. So what am I asking you here? What is the probability that a claim made today is less than $1,000? What am I saying? I'm actually saying I want to know the probability that y is less than 1,000 today. But y is 2x. So saying this is saying this. If you put 2x inside here, then you get x is less than 500. And can you solve this problem for an exponential? Again, use the CDF. I have dumped in the exact number. I didn't use 0.0002, but that's essentially what you got. Put that number value inside here. Put the amount, which is now 500. So this is a good question because it shows you the twists that people can do for an exponential. First of all, they will never tell you the parameter, you have to find it. If I told it to you in a different way, I said the mean claim size 10 years ago was something. What am I telling you? I'm telling you one over lambda is however many dollars. See? There's a variety of ways to ask you what is lambda. This is one way. Telling you that, oh, 25% of claims were less than $1,000 last time. So that gives you the lambda value. Then the question takes another turn where they say, okay, but I'm not interested in claims 10 years ago. I'm interested in claims now. And now we have this information that all claims are twice what they were 10 years ago. And the probability is, what's the probability that claim now is less than $1,000? And you find that, see, it's much lower. It's only 0.134. 10 years ago, claims that were less than $1,000 happened about 1/4 of the time, but now it's different. I think the most important thing to realize, the answer is not half this answer. Okay? That's that's a wrong assumption. You cannot say things like that. You have to work at it from the definition of the problem. Right? So this is, I believe, the law. Oh no, it's not. Okay, let's do another one. Also exponential. A device continuously measures and records seismic activity in a remote region. So there's a lot of earthquakes happening now, both outside the US and in the US. So this will be something like that. Now the time to failure of this device again is exponential. The mean, see, the mean is 3 years. Now, since the device will not be monitored during its first 2 years, the time to discovery of its failure is X. X is max T comma 2. Do you understand why X is max T comma 2? Again, this is not those direct exponential questions. It's a little bit of a twist. Why is the time to discovery of failure the maximum of T at 2? Does anyone know why? That's right. If it failed in year 1.5, you wouldn't know. So the smallest time of failure, all right, the smallest time of failure that you can detect has to be 2. If it failed before that, you would only find out at 2 years, in 2 years time. It says, okay, it's not min T2 is max. You put the machine there, you're not going to look at it, you don't have the resources to go check it for 2 years. Now, you go to the machine after 2 years, and you may actually find, oh no, it's dead. All you can say is the time of failure. I don't know when it failed. It could have been earlier, but the discovery of the failure time would have been 2 years old in that case. If you go after 2 years and find, oh, the machine's still working, then it fails later, then you discover the actual failure time. That's why it's max equal. So determine EX. How do you do that? So again, I want to really emphasize on this because I think the class is a little bit shaky on writing out functions of one variable versus another. First of all, if you know something is exponential, it's not X that's exponential, T. The actual failure time that we are not always privileged to know. That's the point. We don't actually observe T all the time. It's there, but you don't know it. You don't always know it. Depending on when the machine died, you may, I mean, this is kind of a, can I give you a non-morbid example? I have one, but it's quite morbid. Some Okay, let's talk about your home. Okay, maybe someone is robbing your, trying to break into your house right now. But and you go back and discover it's been broken in already. Or sometimes break-ins happen when you are actually in the house, which I don't know whether it's actually worse. Okay, it's even more scary sometimes. So that's exactly what's going on here. This, you would get to observe the failure time if it happened after 2 years. But if it happened before 2 years, you wouldn't know it had failed already. So the actual failure time is not always known. That's exponential. And I'm telling you, the expected value of t is 3 years. This tells you that lambda, the parameter, is 1 over 2. Because for an exponential, the mean is 1 over lambda. So that tells you that the value of lambda is 1 over 3. So does that give you at least the ability to write down the density for t, not for x yet, for t? Now you will notice that I did not ask you for the density function for x. I'm just asking you how to determine the expected value of the time of discovery. And this is the part that you need to pay close attention. Since x is max t2, what does it mean? It means that if t were less than 2, x is 2. This is the point I'm trying to make. Your house was broken in while you were in school. This is the broken in while in school thing. It happened at some time when you were in school, but you only discovered it when you went home. Because x is not the actual time of failure. It is the discovery of the failure. Sometimes if the failure happens after you're home, then the discovery of the failure is equal to the time of failure because you happen to be there when someone broke into your house. But if someone is breaking into your house right now and you're not there, this is this case. You only discover it when you go home. That's the time of discovery. You open the door, oops, something's happening. This is clear. I'm trying, okay? Now, do you agree? This was an exam question. The expected value of this thing. Wow, why did I write it like that? Oh, I know why. Because I put this one first. If you don't like it, please switch positions where it goes on top. This just came more intuitively to me. That's all. How do you find expected values of functions that are weird like that? Go by the zone. So more than 2, more than 2, the function is t. And see the density? Put it in. The 2 to 0 is just 2, and you put the density in. This is the kind of very classic. I don't know whether anyone in this class is interested to do the probability exam, the SOA. This kind of question is very, very, very common in the probability exam. They are not going to ask you a direct exponential question. That's too easy. They will always have a twist where they will link another random variable to an exponential or something. And that's the kind of thing they want to see in order to do. Is this okay? So I'm not, notice, I am not asking you, tell me the density of x. That's a whole nother ball game. I'm not asking for that. I'm saying, can you calculate the expected value of x? That you think. The density of x is not the density of t because x is not t. It's some funky thing that's different, but the expected value you can. Okay? And anyway, numerically, the answer will make sense. The expected time of discovery. So this kind of integration is not trivial. It's quite irritating, but if it's a homework problem, you can always use software. I don't mind. Yeah. Save you time. Please use software if you're doing a homework. I don't mind. Unless you want to practice integration. Some of the integrations are very tedious. I actually recommend you use software. It's very frustrating. Or your calculator or whatever. If you painstakingly went through all the details and finally dumped lambda in, you get an expected time of discovery of about 3.54. Which means what? It's more than 2, which means most of the time this machine is going to fail when you're able to see it. If this were a very small number, it means that it fails very early, and most of the time you didn't get to see it. Okay, it's closer to 2. Okay. Okay, let's look at 176. An insurance policy reimburses dental expenses up to a maximum benefit of 250. The density function for x is this. Okay, sometimes problems are written in this way so that you can recognize the density. Does anyone recognize this density? For this to be a density, what should C be? What does C have to be so that this is a density? 0.004. Why? If I make C 0.004, don't I have the form lambda E minus lambda X? I do. In other words, in not so many words, I'm actually telling you this is the dental expense is modeled as an exponential. Okay. Calculate the median benefit for this policy. Anyone know what median benefit is? Median is the 50% point. So what do you need to do? Anytime you're asked to find some kind of a quantile, the first thing to note is the benefit function is not always x. Again, see the twist? Yes, if your dental expense is less than 250, you get the full thing reimbursed. That's how this insurance plan is. However, if you are unfortunate enough that your dentist charges you more than 250, you are capped at 250. So again, the benefit function is related to an exponential, but it is not exactly an exponential. So how do we do this? We want to find who's responsible, what's the value of the benefit that occurs with 50% probability. That's the median benefit level. The benefit, right? You want to, and ST is such that, okay, you want to find the benefit that 50% of people get the benefit. So the way to do this is to check a few things, okay? You need to see, first of all, whether by the time your dental expense is 250, how many people, what's the fraction of people have a dental expense that's 250 or less, the highest value that you get paid the full amount? If you slowly work this out, or if you can use the CDF, see I'm using the CDF here. This is an exponential with a lambda of 0.004. Using the CDF property, I'm saying that 63% of people have dental expenses, not benefits. 63% of people have dental expenses that are less than 250. What does that tell you about the median benefit? Will it therefore be something below $250? 63% of people have dental charges that are less than 250. That means the benefit, the median benefit, we know is less than 250. So we don't need to worry about that. So all you need to do is go and do. So we know that the probability that, so the median is going to be something less than 250. This whole part is just to establish where is the median. So you can now solve, see, take the CDF of the exponential and set this equal to 50% probability. And then solve. So the median benefit is this. The only wrinkle here is this. Why did I not immediately do this? I had to check something because the benefit function is weird. The benefit function has two branches. If you have an expense that's 250 or less, you get the whole expense. Unfortunately, there's a cap. And you don't know who reaches that cap. So you need to check that first. 63% of people will not cross that cap. So you can safely say, I know that the benefits that people get, the median, will be below 250. So I know which equation I should actually do. All right. And then you solve for, okay, when is this equal to the 50% point? And you solve for that to get $173. So that's the median benefit. 50% of people are reimbursed the full amount actually, because this number is less than 250. Less than 63% of people have dental expenses that cross 250 anyway. So this problem is pretty simple, but we need to establish that. All right. So that's what's going on. Okay. So we will say goodbye to the exponential and now talk about the most famous by far continuous distribution. So this is called the normal, and we will spend, of course, some time talking about this. And I've given you normal table. We'll start using it today. So first of all, what is the normal density? Well, it's this. So pretty ugly, right? But it has some symmetry and beauty about it. We'll point it out. The normal density is a curious one because for any finite intervals, it has no closed form answer. Some infinite intervals you can integrate exactly, but if your intervals are non-infinite, you cannot. Okay. So if you look at this, in contrast to an exponential where there's only a lambda to contend with, the normal density has two parameters. One is called mu, and one is called sigma. It has like two, what's the word I want? Two features, if you like. The exponential just has a lambda. This one has two. There's mu and there's sigma. It so happens that these two have physical interpretation. All right? What is mu? Mu turns out to be the mean. It turns out that this number that sits here turns out it is the mean. It doesn't always have to work this way, you know. Like in an exponential, lambda e minus lambda x, but the mean was 1 over lambda. It's not directly lambda. It's a happy coincidence for a normal that the number mu that appears here coincidentally turns out to be the mean. And if you look at my notes down here, I do say that EX is mean. In other words, a normal density that looks like that has a mean like this. Happily as well, sigma has a physical meaning as well. The variance of x would be sigma squared. So the normal density is mysterious. It contains two parameters that have easily interpretable. I'll tell you what. All right. First, you can always forget about the homogenerating function. Okay, I want you to stare at the density for a bit. And this part of the class is going to turn a little bit mathematical, so bear with me. Look at this density. Do you agree that this is what we call an even function in X? Does anyone in the class know what an even function is? If you know, can you care to define it for the class? What's an even function? Yes. That's right. So this is even in the sense that it's even not at zero, but at mean. So there's a shift of the even function. So let me give you the simplest even function. Y equals x squared is an even function, but it is even at zero. Why? Because at negative x, you square it, you also get the same thing as on the other side. Whether you are here or here, your height. Okay, that's not well drawn. I'm sorry. Right? Whether you are here or here, your height's the same. This is even at zero. If you look at the way the normal density is constructed, it is even about mu. As you travel on either side of mu, and by the way, if you plotted this density, you get the very famous bell curve. where would the middle be? Mu. Does it make sense to you that the middle should be mu? The mean is mu. What have I told you about densities that are symmetric? If you have a density that's symmetric, your mean's in the middle. So it makes perfect sense that the mean should be here. And this is an even function. It is equal height when you are equidistant from me, always. And this can be seen from the equation. So it makes perfect sense why EX has to be mu in the first place. The other thing I want to point out is sigma. If you look at where sigma is placed, sigma is always in the bottom, both here and here. The larger sigma gets, will the density get more peaked or flatter? The larger sigma becomes. As sigma increases, does the density become more focused or actually become more spread out, flatter? Actually, the larger sigma gets, the flatter it becomes. And in other words, a normal density with a large sigma, as opposed to a normal density with a small sigma would look like this. Okay. And does this make sense to you? Because sigma measures what's variance of x. The variance of x is sigma squared. You know that variance is a measure of variability. So when your sigma is big, you are high variability. A high variability normal is, well, very spread out. It's all over the place. A normal distribution with a small sigma is very focused around the. Now, in every case, the normal is defined everywhere. So I'm not saying that this normal distribution ends here. If you drew it like this, it's wrong. Every normal tails off and never touches this axis. It's just that the likelihood of you being in the tail is pretty small if your sigma is small. I mean, if it's a very focused normal, you don't spend much time in the tail. You spend a lot of time. So the moral of the story is the sigma number tells you the standard deviation of your normal. So the normal density is very intuitive in these two respects. It's an even function at mu, because that's where the mean is. And the sigma, which is a function that tells you the number that tells you the spread, sits here. So if your sigma is high, that actually pushes your density flatter and it's more spread out. Higher probability. Okay. So all these things I have mentioned are described in words in your slides, okay? The CDF of a normal is this function. Do you agree? What's a CDF? We have talked about CDFs forever. A CDF is always this probability. And you will see in the ICT I returned, I think some of you got some notation a little bit wrong with the CDF. I want to stress. A CDF is always defined as the probability of you being less than some argument. Now, whether I put T or X doesn't matter. Here I'm using T, and so this would be what FT is. And how do you find that? When you want to find the probability of you being less than or equal to T, you integrate. Integrate what? Integrate the density. Why do I start at minus infinity? Because the integral, the function doesn't change its name everywhere. It doesn't change its name at all. It's always this. So you start from minus infinity, is the lower limit, and you go to the point of interest. Now, what I'm trying to tell you is, unless you choose very special values of t, this thing cannot be evaluated exactly. There is no antiderivative for this function. So the table I have passed out in class is the numerical approximation to this integral. This table is a CDF table that I've given you. And I'm going to teach you in a minute how to use it. All right? This expression cannot be evaluated analytically except for special choices of values like t is mu, t is infinity. You randomly choose some value of t, it's not going to be available for you to do analytically. So, when you have the very special case, when your mu is 0 and your sigma is 1, we have what's called the standard normal. And this is given the symbol N01. The first number is mu, the second number is sigma squared. Mean 0, variance 1. The mean 0, variance 1 table is the table that I have given you. That's the one. Because we can't give you tables for any mu and any sigma squared. There will be uncountably many tables without. The good news is I give you the standard one. Every problem can be reduced to a standard problem. Right? Now, depending on your background, what kind of AP stat you did, some students in high school did. Let me just ask, so first of all, how many of you did statistics in high school? How many of you actually played with a normal table in high school? You did. See? Strangely, at Hope College, the way we teach statistics is students are not exposed to a normal table ordinarily. In my intro stat class, I use it. But there are many professors here who teach it a different way. They completely sidestep this issue. The students don't know what a normal table is. So I don't think any of you, except for one exception, was in any of my intro stat classes. So I'm going to show you how to use it. Okay. So how do you standardize? I'm going to stop talking about this theory. Let's look at an example. Okay. So let X be a normal. Is this the right example to start with? Yes. Let X be a normal random variable with mean 950 and standard deviation 10. Find this probability. Okay. How do we do that? So the first thing to do is to do what's called standardizing. You standardize any variable by subtracting its mean and dividing by its standard deviation, not its variance. So look at like that. This initial problem is 947 to 950. What you do is you take your original 947 and 950 like that, and you subtract throughout the mean of X. So you subtract 950 here, you subtract 950 here, and once you have done that, you also divide by the standard deviation of X, which is 10. Remember this, standardizing is always done by subtracting the mean and dividing by the standard deviation, not the variance. Notice, doing that to X, there's one step which I wish I had written in my slides. Actually, I should have written this as X also minus 950. In fact, when you copy, you should do that. This minus 950, X minus 950 over 10. What you do to the left and the right, you do to the middle as well. So take X, subtract 950, and divide by 10. Do it to everyone. Doing that changes that variable X to what we typically call Z. This is your famous Z statistic. Z is the standard normal 0, 1 random variable. This is not normal 0, 1. This is normal with a mean of 950 and standard deviation of 10. But Z is normal 0, 1. It has been standardized. Then you use your calculator and see what these numbers are. Oh, this is here, this is this, and this is that. Now look at what I'm doing. Your table is formatted as a CDF table. This is not exactly a CDF statement, but it can be rewritten as one. Because saying that Z is between this and this, what are you saying? Aren't you saying this is equal to the probability of z being less than 0 minus the probability of z being less than this. Is this line clear? I think we've not done this a lot. If I say what's the probability of a variable trapped between A and B, aren't I saying less than B, subtract less than A? You draw a picture, draw a number line. Between A and B, between A and B, you can go from B all the way, subtract A all the way, to get B to the middle point. Why am I doing this? Because if I do this, I'm beginning to get it in the form that the table likes. So what is z less than 0? Now, you actually don't need the table for this. You know that the answer has to be 0.5. Why? For a standard normal, the mean is 0. 0 is the midpoint. What's the likelihood of you being less than the midpoint? Half. You know this has to be 0.5. But even if you didn't know, the table helps you. So let me call out our table. I have it on Moodle, of course. But you have a physical copy. I would encourage you to go look at it. It's on here. Okay. Do you see? When your z value of interest is 0, the probability accumulated up to that point is 0.1. If you didn't know, that's how you get the 0.5. I mean, you should know for standard normal, the mean is at 0. Anything up to 0 has a probability of 0.5. So that's how you get the 0.5. Now, what about the other thing? The other thing, you have to work at it a little bit. The table doesn't have negative z's. If you look at the table I gave, it's all positive. So if I ask you a question, z is less than negative 0.3, you have to think about it as, what is this equivalent to? If you, my recommendation is, if this is your first time doing this, draw a small curve to imagine where things are. Less than negative 0.3 is the same as 1 minus z less than 0.3. Why? I'll draw a picture. So your normal curve is here. You want the probability of being less than this. Right? This, due to symmetry, is the same as the probability of you being more than 0.3. Do you agree? Symmetry tells you that this area is this area. Less than negative 0.3, the probability is the same as more than 0.3. Unfortunately, your table doesn't give you this probability. Your table is a less than, so you have to process it a little bit. Therefore, it is 1 minus, in other words, this, I know it's very informal, the area on the right is 1 minus the area on the left. And that is why this is the same as 1 minus the probability of z being less than 0.3. Draw a picture, it will make sense. Once you have it all like that, it's now you can use the table. So look at 0.3. If you go to 0.3 on the table, you should get, see, 6179. Did you see that? And then you work at it like this. Okay. And of course, the rest is just math. You just slowly get the answer like that. Okay, let's try one more. Assume that the time required for a cyclist to travel a distance b is normal, with a mean of 4 minutes and a variance of 4. See, variance of 4. What is the probability that this cyclist will travel this distance in less than 4 minutes? Do you realize why I can tell you immediately that this answer has to be different? Does anyone know why? How do I know this without doing any calculation?
Distributions are centered around
Yes, good. I told you, the cyclist has a mean time of 4 minutes. So the probability that any journey that she or he takes is less than the mean has to be 50%. So it's kind of to check your understanding of what a normal unit is. Okay, what is the probability that this cyclist will travel the distance between 3 minutes and 55 seconds and whatever that is? So you can convert this seconds. That's pretty easy. So basically it's saying what is the probability that he lies between 2:35 and 2:45? So standardize. How do you standardize? You standardize by subtracting oh, wow, I jumped many steps. No, not too many. See what I've done? 235, if you subtract 240, because 4 minutes is 240 seconds, it gives you a -5. Divide by the SE, which is the square root of the variance, so square root of 4. When you standardize, you will turn this variable into a standard normal. Then of course, use your calculator to get this numerical thing. Do the adjustments of what this means, and you get your answer. Right? So what I want you to do for the remainder of the time is actually to solve 179, as many as you can. Okay, tell you what, let's have you do A, B, and C. I don't think that should take you that long, but A, B, and C will be enough. A, B, and C, just to make sure you know how to standardize and use it. Right? And then we're done for today. Just do 179 A, B, and C. We'll cover the other one next. All right? And we're done. So remember that this is not a standard normal. You need to standardize. Standardization is subtract mean, divide by SC, then use table. This will help you to learn how to use the table in different contexts. So if you need help, just let me know. All right.